Hi everyone, welcome back. My name is Anand, and today we're going to be talking about trees and heaps. So trees are a hierarchical data structure that are comprised of nodes, where each node stores its own value and pointers to its children. And the types of nodes or terminology we'll be using today are root node, which represents the first node in a tree, the parent and children, where the parent is simply above the nodes it connects to below. So for example, 1 is the parent of 9. And finally, we have leaf nodes, where leaves are just nodes without any more children, and therefore end a traversal at that side of the tree. The reason we use tree data structures are to model hierarchical data, and the most intuitive example would be a family tree, where each node or pair of nodes are spouses and their children are their corresponding left and right child. Trees also offer efficient insert and search solutions that are going to perform in big O of log n. Some sample code to represent a node class in a tree includes just the data, which in this case is an integer, and a pointer to its left and right children. Finally, when we introduce some constraints to our tree, we come up with the different types, and the two most popular or common ones include the binary tree and the binary search tree, where the binary tree simply constrains each node to having at most 2 children. So one's left child and right child are 7 and 9, and it can have no more than that. The binary search tree builds upon this by introducing an additional constraint that the left child's value has to be less than the parent and the right child's value has to be greater than the parent. So we can see here at the root, all the values or nodes that are greater than 8 have to be in the right subtree of 8. So everything greater than 8 has to be on its right, including 10, 14, and 13. And everything less than 8 comes out on its left. So as you can see, this applies not just to the direct nodes, where 10 and 3 have to follow this, but all subsequent nodes, forming the whole binary search tree. When we talk about insertion and deletion within a binary search tree, we have a few different scenarios, but insertion is quite simple, where we have to simply traverse to a leaf and add. Now, we know that a leaf is any one of these nodes here at the bottom, where we have no more children being attached to them. But the way we get to the bottom of a tree or to the leaf of a tree is by traversing, where we only store a reference to our root node, similar to a linked list where we have just a reference to the head. In a BST or any tree, we always store a reference to the root. And from the root, we can either go left or right when traversing to a value. So if I were to search for the value 13, I would start at the root at 8, compare 13 to 8. Since it's greater, I would go right. And then 13 is greater than 10, so we again go right one more time. Then finally, 13 is less than 14, so we go left. And this allows us to reach the bottom of the tree where our value is equal to 13. Now, if we were going to insert a node, say 5, we have to traverse to the corresponding leaf and add it as a child. So in this case, since we're looking for 5, we'll start at the root, go left because 5 is less than 8. 5 is greater than 3, so it has to be in the right of 3, where we go down all the way to 6. And now 5 is less than 6, so we come down to 4. And now we've reached a leaf. There's no more nodes to traverse, so we simply add it as a child of 4. Upwards, not downwards. And this here is a good visualization of a tree being constructed with nodes being added sequentially. And finally, for deletion, we have a little bit more of a complicated scenario. And our issue is that we don't want to invalidate any of the tree's properties. So if I'm saying delete 3 from this tree, I can easily search for it like we just did, starting at 8, coming down to 3. And since we found 3, we think that we can just get rid of this pointer and 3 is gone. But if we do so, we get rid of 3, 1, 6, 4, and 7, and everything in its subtree, which is not good and will lead to data loss. So to handle this, we have three different scenarios, where the first one is if we are deleting a leaf node, which is the easiest. So if I'm deleting 1, for example, I can search for 1. So I start at the root, 8, 1 is less than 8, go left, 3 is less than 1, and 3's left child is equal to 1. So what we'll do in this case is take 3, set its left pointer to null, and just chop this off. And 1 still may exist in memory, but because it doesn't have a direct pointer from 3, it is not in the tree anymore, which is all we care about. Next, we have the situation where we're deleting a node that has only one child. So, for example, if we were deleting 10, then we would come to 10, we see that it doesn't have a left child, and it does have a right child. So our only option is to promote this 14 right here to be the right tree or right node of 8. So this would look something like this. And now we still have a valid subtree where 14 is greater than 8, 13 is greater than 8, and we've successfully removed the node with the value 10. Finally, when we're deleting a node that has two children, we're going to use something called the in-order successor to replace the node we're trying to delete. And the in-order successor is defined as the next smallest node in the tree, and the way we'll find it is by going to the leftmost node in the right subtree. So if I was deleting the node 3, which has children 1 and 6, I'm going to find its in-order successor, which is the leftmost node in the right subtree, so the leftmost node in here. And what we do is we traverse to 6 and go all the way left until we hit a leaf. So in this case, it's very simple. We end up here pretty quickly. We just get 4 is our in-order successor. And now that we have 4 as the in-order successor, we're simply going to remove it from here and put it up here. So instead of 3, this will be replaced with 4. And as we can see, this maintains the validity of the tree. We have the root, and we check going down. 4 is less than 8. 4 is greater than 1 and less than 6. So by using the in-order successor to delete the node 3, we've maintained the validity of and the properties of the tree. Now for some practice, you guys can try to pause the video and insert nodes 10 and 20 to the following BSD. And the way we'll be doing this is simply by traversing to a leaf and adding the nodes. So what this will look like is we're going to search for 10. So 10 is greater than 5, we traverse to the left subtree. 10 is less than 19, we traverse to the left subtree. Now we've hit a leaf, so we're going to add 10 to the right of 9. So now we get this. Next, if we're adding the node 20, we're going to again search for it. So 20 is greater than 5, we traverse right. 20 is greater than 19, but 19's right node is null, so we insert 20 here. Finally, to briefly cover what a heap is nothing more than a tree with some more additional constraints. And we have a max heap and a min heap, where a max heap has the property that the parent has to have a value that is greater than or equal to both of its children. And the min heap is the opposite, where the parent must be less than the children. And something you'll note on the bottom here is that heaps and trees can also be represented as arrays, where we use the index with the formula to define which are the corresponding left and right children of the earlier indices. And the reason we use heaps are for applications or algorithms where we have frequent min-max calculations, since if you notice in a max heap, we're always going to have the highest value at the root, and the min heap will be the opposite. Finally, to recap, we learned that is a hierarchical data structure that is comprised of a node with a data and corresponding children. And we learned several types of trees, including the binary tree, binary search tree, and heaps. And as we continue, if you understand what a tree is at its core and some of the most basic ones, you'll realize that all of the other types of trees are simply additional constraints added to the original one. And if you understand the base version, you can understand all of them. That's all for today, and I'll see you guys in the next one.